Let's take a look at section 8.2, simplifying radicals. We want to use the product rule for square roots, which says if the square root of a and the square root of b are real numbers, then the square root of a times b equals the square root of a times the square root of b. So let's look at using this. If I have the square root of 5 times the square root of 3, this product rule tells me that's the square root of 5 times 3, which is the square root of 15. When a square root is applied to an imperfect square root, we will often use the product rule of radicals to simplify such a square root. So the square root of 8 can be written as the square root of 4 times 2. Since 4 is a perfect square, we'll write this as the square root of 4 times the square root of 2, and we'll evaluate the square root of 4, which is 2. So this simplifies to the 2 times the square root of 2. So that's how I would simplify the square root of 8. And remember to check the remaining radical to see if it can be simplified further. Here, the square root of 2 can't be further simplified, so 2 times the square root of 2 is the final answer. So let's look at simplifying the square root of 75. So I want to know what's the largest perfect square factor of 75. Well, I need to write the perfect squares. I start by squaring 2, then I square 3, I square 4, I square 5, square 6, and so on. So 4, 9, 16, 25, 36, and so on are my perfect squares. I see that 25 divides evenly into 75, so I'm going to write the square root of 75 as the square root of 25 times 3. And that equals, according to the product rule, the square root of 25 times the square root of 3. When I evaluate the square root of 25, I get 5 times the square root of 3 as my final answer. So I want to evaluate or simplify the square root of 300. Now I notice 4 and 25, as well as 100, are perfect squares that divide evenly into 300. I want the largest perfect square if there's more than one that divide evenly into my radican. So I rewrite this as the square root of 100 times the square root of 3, which simplifies to 10 square root 3. So the quotient rule says if the square root of a and the square root of b are real numbers and b is not 0, then the square root of a over b is the same as the square root of a over the square root of b. So let's use this quotient rule to simplify the square root of 75 over the square root of 49. Well, this can be thought of as the square root of 75 over the square root of 49. And we already saw how to simplify the square root of 75. I write it as square root of 25 times the square root of 3, and that becomes 5 square root of 3. The square root of 49 is 7. So let's simplify the square root of 25 over the square root of 49. That would be 5 over 7. I apply the square root to the numerator and to the denominator. The square root of 700 over the square root of 36 is the square root of 100 times the square root of 7 over the square root of 36. Notice 100 is the largest perfect square factor of 700. So this, I evaluate the perfect square roots of the perfect squares, and I get 10 square root of 7 over 6. And now I need to reduce 10 over 6. Both 10 and 6 can be evenly divided by 2. 10 divided by 2 is 5. 6 divided by 2 is 3. So this is 5 square root 7 over 3.
To simplify square roots involving variables, use the product rule and quotient rule in basically the same way as with numbers. Split the radicand into two factors where one of the factors is the largest perfect square factor of the radicand.
So the square root of y to the 16th, y to the 15th is y to the 14th, the square root of y to the 14th times y. The product rule says I can write that as, and notice anytime I'm taking a square root of an exponential, if the power is divisible by 2, then that exponential is a perfect square. 15 is not evenly divisible by 2. 2 is my index of my radical. It's unwritten. So I rewrite y to the 15th as y to the 14th times y. I apply the square root to y to the 14th to get y to the 7th, and that's multiplied by the square root of y. All right, so here I have the square root of x to the 35th. I'm going to write that as x to the 34th times x. So I'm rewriting the radical as square root of x to the 34th times square root of x. When I apply the square root to x to the 34th, I'm dividing the index of 2 into 34 to get that the square root of x to the 34th is x to the 17th. And then that's multiplied times the square root of x. All right, the square root of 75, recall we rewrote that as the square root of 25 times the square root of 3. And now we're going to rewrite x to the 35th as we did above, as x to the 34th, which is a perfect square, times x. And then y to the 14th is a perfect square since my index of 2 divides evenly into that 14. So let's evaluate the square root of the perfect squares. Square root of 25 is 5. Square root of x to the 34th is x to the 17th. Square root of y to the 14th is y to the 7th. And notice that this is multiplied times the square root of 3x. All right, so here I'm just combining, I'm doing what I've already done. My numerator is exactly what I was simplifying in number 10. So I'm going to do the exact same process to simplify this square root that's in the numerator. And now I have a denominator, square root of 36z to the 8th, which is a perfect square. Since 2 divides evenly into 8, z to the 8th is a perfect square. So my numerator is simplified exactly as it was in when I was working it as a simple problem in number 10. And now I apply the square root to 36z to the 8th to get 6z to the 4th. And notice the index is 2, so I divide that power of 8 on z by 2 when I evaluate that radical. So let's look at simplifying higher roots. If the nth root of a is simplified if the radicand A has no factors that are perfect nth powers other than 1 or -1. The index of the radical determines how we should factor the radicand. General forms of the product and quotient rules are given. The product rule: if the nth root of A and the nth root of B are real numbers, then the nth root of A times B is the nth root of A times the nth root of B. The quotient rule for radicals says if the nth root of A and the nth root of B are real numbers and B is not 0, then the nth root of A over B is the same as the nth root of A over the nth root of B. So let's simplify number 15. So here we look at the index of our radical, which is 5. So we're interested in perfect fifth powers. So we start by we get our first number on the list by raising 2 to the 5th. And that is 32. Then we raise 3 to the 5th. Which is 243. Then we raise 4 to the 5th, which is 1024. So these numbers get large really quickly. And we want to rewrite 64 as one of the numbers on this list, if possible, and some other number. Well, 32 times 2 is 64, and 32 is on my list. That goes in my first radical. I put all my perfect fifth powers in the first radical. Now I look at x to this power and I see that x to the 11th is not a perfect fifth power because 5 doesn't divide evenly into 11. So I rewrite x to the 11th as x to the 10th times x. 5 does divide evenly into 10. Similarly, I rewrite y to the 17th as y to the 15th times y squared. Since 5 divides evenly into 15, y to the 15th is a perfect fifth power. I rewrite z to the 34th as z to the 30th times z to the 4th. In a fifth root that's simplified, exponentials can only have powers that are smaller than 5. So the only allowed powers would be 1, 2, and 3, and 4 in a fifth root that's simplified. So now let's evaluate the fifth root of the perfect fifth power. Fifth root of 32 is 2. Fifth root of x to the 10th is x to the 10 divided by the index 5. So 10 divided by 5 is 2. That's the power that goes on x. 15 divided by 5 is 3. 30 divided by 5 is 6. So those are the powers that go on x, y, and z. And then this is multiplied times the fifth root of 2xy squared z to the 4th. So that's how I would simplify that problem. Now we're dealing with the fourth root. So we're interested in perfect fourth powers. So I begin by raising 2 to the 4th. And that's 16. That's the smallest number on my list of perfect fourth powers. 3 to the 4th is 81. 4 to the 4th is 256. And so forth and so on. So I noticed that in this particular example, 32 can be rewritten as 16, which is one of my perfect fourth powers, times 2. So I always want one of the factors to be on my list of perfect nth powers. The power on x is x to the 13th is rewritten as x to the 12th times x. Y to the 23rd is rewritten as y to the 20th times 3. Z to the 30th is rewritten as z to the 28th times z squared. Now notice that the powers, my exponential is a perfect fourth power if its power is divisible by 4. And I recopy the denominator, which is a perfect fourth power. So now I'm going to evaluate the perfect fourth powers to the fourth root of the perfect fourth powers. Fourth root of 16 is 2. Fourth root of x to the 12th is x cubed. I get that by dividing 12 by the index 4. Fourth root of y to the 20th is y to the 5th. Fourth root of z to the 28th is z to the 7th. I recopy the fourth root of 2xy cubed z squared. And then I apply the fourth root of 81 w to the 8 to 80. I take the fourth root of 81 w to the 8 to get 3w squared. And let's look at our final problem where we're dealing with the cube root. We want to look at our perfect cubes. We begin by cubing 2, we get 8. Cube 3, we get 27. Cube 4, we get 64. Cube 5, and we get 125. But we notice with this problem, we want to first use the quotient rule, since we can actually divide that denominator's radicand into the numerator's radicand. So the quotient rule says I can divide first if that makes my work easier. So I'm going to first divide 128 x to the 13th y to the 23rd z to the 30th by 2x to the 8th. So, and my radicand becomes 64 x to the 5th y to the 23rd z to the 30th. Remember, x to the 13th divided by x to the 8th is x to the 13 minus 8, which is 5. Now, this entire expression is not a perfect cube, so I'm going to use factoring and the product rule. 64 is a perfect cube, but x to the 5th isn't. So I write x to the 5th as x cubed times x squared. Y to the 23rd is not a perfect square, so I write it as y to the 21st times y squared. Since the index 3 divides evenly into 21, y to the 21st is a perfect cube. And z to the 30th is a perfect cube. And now I evaluate the cube root of the perfect cube. Cube root of 64 is 4. Cube root of x cubed is x. Cube root of y to the 21st is y to the 21 over 3, which is y to the 7th. And the cube root of z to the 30th is z to the 30th divided by 3, which is z to the 10th. And I multiply that by the cube root of x squared y squared.